folks, Mr. G here with another educational video. Today we're doing something a little bit different. Instead of me just going through the notes and you just copying down all the stuff that's written in red, today we're going to be doing a bit of an interactive or a walkthrough lesson. So make sure that you have the blank notes with you, so either print it off or maybe you have them digitally, whatever you prefer. And as we go through this, I'm going to be asking you at different points to pause the video, read through the notes, and then try out the questions on your own. We'll go through them afterwards together. So to start off here, we're going to be talking all about Earth science, in particular about Earth's continents and the different layers. So do you think that Earth continents stay the same or are they changing and moving? Make a prediction. Some of you might know the answer to this question, but make your prediction right here, right now. Well, let's take a look at some evidence that might help us decide whether or not Earth's continents stay the same or change and move. So our first observation here is that Antarctica is frozen. So that's deep south. It's so cold and icy that no trees can grow there right now. But scientists have discovered fossils, remains that have been preserved in rock of ancient trees in Antarctica. What do you think this means? Pause the video and write down what you think it means. So if Antarctica is frozen and no trees can grow there, yet we've found remains of old trees, this means that Antarctica used to be located in a much warmer climate. It wasn't always this cold in order for ancient trees to have grown there. The Himalayas, which are mountains in Central Asia, are the tallest in the world, but fossils of seashells can be found high in these mountains, far away from any ocean. How do you think they got there? Pause the video and write what you think. That means that at some point the rock got pushed up to form the mountains that we see today. Now here's a map of the world right now, and these white spots here are places where there's evidence of glaciers, ancient glaciers. And they're expanding out in the directions that are shown in these arrows here. Now we can sort of reconstruct these and put these back together using this picture down here. And where do you think the center of our ice cap once was? A, B, C, or D? In this case, it's going to be at C. We can see that this is where all of the arrows are pointing out from. So this is the place where all of the arrows are pointing out. So notice our glacier was once in the middle of Africa, where there aren't any glaciers today. So these bits of evidence, along with some others, convinced Alfred Wegener, a German scientist who wondered about Earth's continents and whether they stayed the same. He found some other observations that you can read down here. Once you're done reading these, take a look at the question at the bottom of the page here. Pause the video and try and answer, based on these observations, what inference could we make about the continents? All done? Well, all of these continents, it seems like there's evidence that they were once together, because we can see evidence of the same things happening on different continents that are now apart. So Alfred Wegener was also convinced by this. He saw this evidence in 1912 and proposed something called the Continental Drift Theory, that about 200 million years ago, all the continents were connected in a supercontinent called Pangaea, meaning all the world. Over time, they slowly moved apart. I'd encourage you to click on this link right here. So you can do that on the electronic version or search up continental drift and click on this animation. It'll show you how the continents once fit together and then how it spread out into the continents we know today. Now for a long time, scientists in general rejected Wegener and his theory because there was no explanation as to how the continents would move. It wasn't until the 1970s that they could accept it because we found some new evidence about Earth's layers. So right now, I'd like you to read this section here about Earth's layers, all the different parts. We've got these four main parts here. And then answer the question at the bottom here. Finished reading? Well, of these four parts, we know that the upper part, the crust, is the stuff that we're standing on. But this lower part here, the mantle, is like a soft taffy. And this is the part that must be able to move. So the middle of our mantle is made up of a rock like soft taffy, so it can flow and slowly move. If this part of the Earth moves, then this could allow our continents to drift as it floats on top of our mantle. Let's talk a little bit about the ocean floor. Take a moment now to read through this, watch this video, and look at some of the diagrams here about how mid-ocean ridges can be formed by rifts in the Earth's crust beneath the ocean. When you're done that, take a look at this next page and answer the first two questions here. All done? So how did discoveries of mid-ocean ridges and the ages of ocean rock support Wegener's theory of continental drift? Well, these discoveries show that Earth is changing and the rock beneath the ocean does move. Wegener thought that the continents moved, but he didn't know how they did. This was a piece of evidence showing how one part of how rocks can move. We see that over time, this mid-ocean ridge pushes rock out. We get new rock near the ridge and old rock away from the ridge. This is evidence that our crust can move and change. One good sentence to summarize seafloor spreading. Your sentence might look a little bit different, and that's okay. The magma beneath the crust moves up into the space between two of our plates, which causes the plates to be pushed apart from each other. So that's what's happening in our diagrams here. As this magma from our mantle is being pushed upwards, it pushes our two plates in other directions, the two bits of crust here, which causes them to move, and we create new crust in the middle here. Now take a look at this graph. And after you've read through the graph and looked through it here, try and answer the rest of the questions on this page. All done? All right, let's take a look at our graph here. It shows us the age of our seafloor and the distance from our ridge, and we can see that it's a linear relation that's increasing here. So as the distance increases, the age increases. So looking at our ridge here, what is the age of the oldest and the youngest rock? Well, those are all of our data points in blue here. So our oldest rock here is just about a little more than 100 million years old, about 110 million years. And our youngest is all the way down here, maybe around 13, 14 million years old. If you had slightly different numbers, don't worry about that too much. If we wanted to find where along our mid-ocean ridge you'd have to travel so you found rocks that are 60 million years old, well, we look at our age, 60 million, we can see that our line here, it lines up a little bit between 800 and 1,000, so about 900 kilometers away from our mid-ocean ridge. We already described a little bit before the age and how it's related to the distance. So as they get away from our mid-ocean ridge, the rocks get older. So farther distance, older rocks. So what conclusion could we draw from our graph here? The further from our ridge we get, the older the rocks are. That's the pattern we see here. And that makes sense with what we understand already about how the magma pushes our rocks away and creates new rocks in the middle. So we have new rocks here and old rocks far away. Finally, why was there so little evidence about these oceans during the time Wegener was collecting evidence? So back in 1910, 1920, why was it possible to learn so much more after the 1940s? Well, the key thing here is that we didn't have a technology to observe the bottom of the ocean, things like sonar and submarines. So after the 1940s, we had sonar and submarines that allowed us to go down and see the mid-ocean ridges and map out the ocean floor. Finally, let's talk a little bit about plate tectonics. So plate tectonic theory is this theory about how our different plates, the different plates that make up the Earth, move around and shift and change. So read through this here and take a look at this picture. And in particular, look at how this picture matches up with this picture right here showing activity from volcanoes and earthquakes. Once you've done that, answer all of these questions on the following page. Pause the video and see if you can answer them. So our image 4.7, we see the image of our plates as well as where all of our volcanoes and earthquakes are happening. And what you might notice is that we have very strong relationship or very strong correlation for the edges of these plates and then where our volcanoes and earthquakes are. So earthquakes and volcanoes tend to occur at the edge of these plate boundaries. So the inference we could make about this is that these plates interacting with each other must cause earthquakes and volcanoes. And we're going to learn about that more later in the lessons of this unit, why this happens and how it happens. Now let's think about plate tectonics and continental drift. Continental drift was the theory that Wegener came up with in 1910. Plate tectonics is the more recent theory, the one that came out or was developed in the 1970s after we had access to things like submarines and sonar. So continental drift says that the continents are once connected and drifted apart, but doesn't explain how or why. Plate tectonics tell us that continents are made of large plates that float on top of our mantle, and this explains our continental drift theory. So plate tectonics is sort of the next step in our theory that can explain continental drift, as well as other geological activity like earthquakes, volcanoes, and mountains. Now you might have noticed at Lord Byng we recently had a large amount of construction, particularly behind the school near the tennis courts. And this was all to make our building earthquake safe. Why would it be important for buildings in Vancouver to be earthquake safe? Well, if we look at our picture, we live right on the edge here of the North American plate. What that tells us from our picture here, we can see that there are lots of instances of both volcanoes as well as earthquakes around here. So it's going to be important because we're right near the edge of the North American plate, and we expect a lot of earthquakes in Vancouver. So it's important that our buildings are safe in the event of an earthquake and they don't just collapse. Would it be as important for buildings in Saskatchewan to be earthquake safe? Why or why not? Well, if we look at where Saskatchewan is on our picture, it's in the middle of Canada. So it would be somewhere around here. You'll see we're very far away from any plate boundary in the middle of Saskatchewan, so we wouldn't really expect to have earthquakes. So it wouldn't be as important for Saskatchewan to have buildings that are earthquake safe because it's far away from anywhere we would expect to get earthquakes. It's not close to any plate boundaries. So take a moment right now and read through this back page here, talking a little bit about the theory of science, how scientists who contributed to this theory were taught very different things in school. So look up the meaning of the word fact, think of a fact you learned recently, and then write down these I wonder questions. Pause the video, and then we'll go over it together in a moment here. So if you look up the definition of the word fact, you might get different things depending on where you look. A fact is something most people consider to be known or proven true. So they can be defined as observations, and a fact can change when we learn that it is no longer true. This usually comes with technological advances or more information that allow us to make observations we couldn't make before. So in science, things that science tells us are facts may eventually be disproven, and a new explanation will have to be developed, and this happens all the time in science. One thing to note that is if a fact is something that is known or proven to be true, then how could our facts change? How could something that is proved to be true, such as continents don't move, suddenly not be a fact anymore? Well, this tells us that science and scientific discoveries are always happening, and that our information and our theories are always changing. And that's okay. That's how we move forward in science. We don't have the explanation for everything, but if we keep moving forward, asking questions and finding answers, finding old facts we thought were true that are no longer true, this is how we advance our scientific knowledge. Could you think of a fact that you learned recently? Maybe think of what sort of discovery could make you question whether it's a fact. One thing that I was thinking about was our conversation about the speed of light. So you learned recently that the speed of light is 30 million meters per second. Now that's something that we've known for a number of years, decades even. But recently, there were some experiments that said that neutrinos or other particles could travel faster than the speed of light. Now, it turned out that those observations weren't actually properly done, that there were some errors in their experiment. That's definitely an example of a fact that you all learned recently, as well as a discovery that could make you question whether it's a fact or not. Right? If we discovered something that moved faster than the speed of light, suddenly this idea that the speed of light is the fastest you can go, suddenly that fact isn't a fact anymore, and we have to come up with something new. Finally, there's lots of things you could wonder about when learning about plate tectonics. Maybe you're wondering about how plate tectonics explain volcanoes and earthquakes and mountains. Maybe you're wondering about how the different layers of Earth are related to one another, why we have different layers, what the different layers, what their properties are. All of these sorts of things we're actually going to be learning about in the coming lessons. So take some time and write down at least one I wonder question, and then see if you can find some answers online or by asking others that you know. If you can't find the answer to your question, stay tuned. You might find it in some of the lessons coming up that we have here. If not, post it in our Extra Super Cool Science channel or in the Questions and Answers channel, and let's see if we can come up with an answer together. That's the end of our video here. I hope you enjoyed this interactive style, and I hope you engaged with it, trying out the questions on your own and not just copying down what I have here. Before you finish up with your science work today, don't forget to check Teams for any other homework or assignments or announcements for the day, and I will see you all in the next video.